This is lecture 4E. Last time we were learning how to write a rate law expression for a chemical reaction. If we want to write the rate law for the reaction A yields B, a rate law is an algebraic expression that shows what factors influence how fast this chemical reaction goes. And the rate of a particular reaction is going to be proportional to two things. When we write our rate law, we say the rate of the reaction equals a constant multiplied by, in this case, the concentration of A raised to some unknown x. The rate of the reaction depends upon two things here. The K is a constant called the specific rate constant, which is proportional to temperature. If you raise the temperature, you raise the value for K, that means the reaction. The brackets A stands for the concentration of the reactant, in this case only one reactant A, and if you concentration react A, you're going to get the rate to increase as well. The reason for this has to do with collision theory. We believe reactions occur by having molecules collide, and they have to collide with a sufficient amount of energy to cause an effective reaction to take place. So how do you make lots of collisions? Well, you can raise the temperature because that increases the speed of the molecules. They're going to be colliding with each other more often. So that's why an increase in temperature will raise the rate of a reaction. And if you have more A molecules in the container, the chances of them colliding has increased, and that's going to cause a greater number of collisions, therefore more reactions occurring per second and a faster rate. Now, the concentration of the reactant affects the rate in several different ways. It all depends what the exponent is in which A must be raised to, and we call that the order of the reaction. And if we have a rate law, the most likely orders are 0, 1, and 2. The rate could equal K multiplied by the concentration of A to the 0 power. The rate could equal K multiplied by the concentration of A to the first power. Or the rate could be proportional to K multiplied by the concentration of A raised to the second power. So for each of these different orders, whichever one is correct, we would have to determine experimentally, we can write a rate law. If it's to the 0th power, A to the 0th power is 1, we would just say the rate of the reaction equals a constant. It's always constant no matter what happens. There's an equality statement that we can write based upon this rate law, and you're going to need to know this. If a reaction is 0 order with respect to a reactant, then the concentration of that reactant, in this case the concentration of A at time t, will always equal the negative of the specific rate constant multiplied by t plus the initial concentration of the reactant A. If this equality is true for 0 order kinetics, and you might recognize it's the form y equals mx plus b, then that means if you plot the concentration of A versus time, you're going to get a straight line where the slope is going to be negative k, and the intercept, the y-intercept, is going to be the initial concentration of A. So for all 0 order reactions, there will be a linear plot you can make if you graph the concentration of the reactant versus time. If you have a first order reaction where the rate of the reaction is proportional to the reactant A's concentration to the first power, then an equality statement that is determined from this particular rate law is a little bit different. It turns out that the natural log of the concentration of the reactant A at time t is going to equal negative kT plus the natural log of the concentration of the reactant A initially. This also fits the form y equals mx plus b, but for first order kinetics, a linear plot will be produced if you graph the natural log of the concentration of A versus time. The slope again will be negative k. This time the intercept will be the natural log of the initial concentration of A in the container. If the reaction is second order with respect to A, the rate law would look like this, and an equality statement that can be derived from that rate law is 1 over the concentration of A at time t will equal positive kT plus 1 over the concentration of A initially. This once again is y equals mx plus b. So if we graph the reciprocal of the concentration of A versus t, then the slope will be positive k, and the intercept will be 1 over the initial concentration of A naught. So the three rate laws, which we determined experimentally from data that we talked about in our last lecture, will lead to an equality statement, and you'll need to know the three different equality statements that correlate to the rate laws. And then from those equality statements, you can deduce what would create a linear plot. We're going to use that to our advantage to be able to determine rate laws from different types of data, and we're going to try that now. I want to see if we can figure out what is the correct rate law for this reaction, A goes to B, given the following data. And what I'm going to give you today is different from last time. I'm going to measure experimentally the concentration of A at different times. What's different about this data from the previous lecture we did is that we were measuring the initial rate of a reaction given initial concentrations. From that data, we can determine the rate law. We did that in lecture 4D. But what if we do something different? What if we just measure the concentration of a reactant as a reaction progresses? Let's say initially at time 0, the molarity of A is 0.2500. We let the reaction run for 5 seconds. We find the molarity of A has gone down to 0.1250 molar. We let the reaction run for 15 total seconds. The concentration of A has gone down to 0.0625 molar. So this is a different type of data. If we're going to calculate a rate law from this data, then we're actually going to need to figure out the exponent, which is x, and it's going to be done in a different fashion than we did before. We're not going to plug values from different experiments into the rate law because I can't do that. I don't have rates. I don't have any R value to plug in there. So here's what we're going to do instead. If you're given concentration of a reactant versus time, or it could be concentration of a product versus time, then you're going to test for each of the different orders. How do you test for an order? You have to know what makes a linear plot. So if we're going to test for zero order, the graph that would make a line for zero order kinetics would be the plot of the concentration of A versus T. So we have to test these three data points, the given molarities with times, and see if they lie in a straight line. Now, if you have Excel, you can plug the three values, the three coordinate pairs in there, the molarity of 0.2500 at time 0, the molarity of 0.1250 at time 5, and the molarity of 0.0625 at time 15, and see if the 3 points wind up making a perfect line. If you don't have Excel, we'll do a little algebraic way where you can predict whether these 3 points lie in a line. If they lie in a straight line, then if I calculate the slope between my first two ordered pairs, and then I calculate the slope between the second and third ordered pairs, if all the points lie in a line, then the slopes will be the same. So if linear, a slope calculated with any 2 points will always be constant. So let's try that. Let's take the first two data points, time 0, time 5, and calculate what the slope would be if those two were plotted A versus T. Slope is difference in y's over difference in x's. So the y values, which is going to be our concentration of A, we're going to go 0.2500 minus 0.1250 to get my delta y. And then my delta x is going to be 0 minus 5. This is difference in y's over difference in x's. If I calculate this out, I'm going to get the slope that would be the slope of the line that connects those 2 points. The units will be molarity per second. The molarities don't cancel out when you subtract, right? 0.25 molar minus 0.125 molar is 0.125 molar, and the denominator is going to be negative 5 seconds, and so the units will be molarity per second. I get a slope between these 2 points of negative 0.0250, which is fine. Now you have to pick another set of points, and I can pick points 1 and 3, but I'm going to instead pick points 2 and 3 and calculate the slope of the line that connects the second 2 points. So I'm going to go my difference in y's, 0.1250 minus 0.0625, divided by difference in x's, 5.00 minus 15.00, and I'll calculate the slope of the line that connects these 2 points. The units will be molarity per second, and in this case, it comes out negative 0.00625. So these slopes are not the same. That means the 3 points cannot lie in a line. If the slopes are not constant, that means it can't be a linear graph, therefore it's not zero order. So we've concluded that in the rate law, it is not rate equals K times concentration of A to the 0 power. Next, let's test for first order. If it's first order kinetics, we know that a linear plot would come from graphing the natural log of the concentration of A versus time. So I'm going to do the same thing. I'm going to take two sets of points, and I'm going to calculate what the slope would be if I plot natural log of A versus time. So let's take our first 2 points, time 0 and time 5. In the numerator, my difference in y's would be natural log of 0.2500 minus natural log of 0.1250. The denominator would still be difference in x's, the difference in times, that would be 0 minus 5. So now I can calculate what the slope would be if I'm graphing natural log of A versus time. Now, when you take the natural log of a number that has units, the units disappear. So in this case, the numerator has no units. The natural log of a number does not have a unit. So there's no units on the top, there's seconds in the denominator, so the units will be seconds to the minus 1. This number comes out to be negative 0.139 seconds to the minus 1, so that's the slope of the line connecting the first 2 points if we're graphing natural log of A versus t. Let's do the second and third points. So I'm going to take my difference in y's, which will be the natural log of 0.1250 minus the natural log of 0.0625, and divide it by the difference in x's, 5 minus 15. Again, the units will come out seconds to the minus 1, and this time the slope turns out to be negative 0.0693 seconds to the minus 1. These two slopes are not the same. That means the 3 points cannot lie on a line. So if the slopes are not constant, the 3 points are not linear, and if they're not linear, it is not first order. So we've deduced that the rate law is not rate equals k times concentration of A to the first power. Let's test for second order. And if it's going to be second order, a linear graph comes from graphing the reciprocal of the concentration of A versus time. And so once again, I'm going to test sets of points, calculate what the slopes are between those sets of points, and see if they're constant. I'm hoping it's going to work out this time because this is the last thing we can test. So for my reciprocals, I'm going to go 1 over 0.2500 minus 1 over 0.1250. And in the denominator, it's the difference in times, 0 minus 5. Now, the numerator does have a unit now. The numerator has a unit of 1 over molarity, or molarity to the minus 1. And we have seconds in the denominator, so that's going to be seconds to the minus 1. So the final units of our slope is going to be molarity to the minus 1 seconds to the minus 1. And if you calculate it, it comes out 0.800. If I take my second 2 points, and I subtract the reciprocal of the molarities and divide it by the difference of the 2 times, it's 1 over 0.1250 molar minus 1 over 0.0625 molar divided by 5 minus 15. My units again come out molarity to the minus 1 seconds to the minus 1, and numerically it comes out 0.800. Now, these are exactly the same. The only way the slopes are going to come out the same is if all the points, all the data points, lie in a straight line. So if the slopes are constant, that means that the reaction must be second order, because a second order kinetics reaction always will have a linear slope if you graph the reciprocal of the concentration of the reactant versus time. And so therefore, we can conclude that the rate law is rate equals k times concentration of A squared. So in our last lecture, we learned how to calculate rate laws by given initial rates and initial concentrations. In this lecture now, if you're given experimental data, that's the concentration of a reactant and how it varies with time, the way you get the rate law is by testing the linear plots for zero order, first order, or second order. So for our reaction, A goes to B. If the rate law for this reaction turned out to be rate equals K, that would be a zero order reaction, because this would be the same as writing rate equals K times concentration of A to the 0 power. So we call this a zero order reaction, and the way we abbreviate a zero order reaction is we say 0 with a superscript naught. So that's zero order. So what does a rate mean? A rate is how fast the reactant reacts away per time, or how fast the product is produced per time. If I want to express the rate of this reaction by how fast our reactant reacts away, I would write it like this. The rate is the amount of disappearance of the concentration of A per unit time, where the D's stand for infinitesimally small amounts of unit time. So that's a more fancy way to write RATE. You could always write the rate law as this, as what's on the left side of the equation. And it's going to equal K multiplied by the concentration of A to the 0 power. Now, how do we get for zero order kinetics our equality statement that we showed at the beginning of the lecture and therefore get our linear plot? Well, to do that, you have to know a little bit of calculus. So if you've had calculus, this might actually be really good for you because you're going to see a real application of something you've learned, because quite often when you're taking math classes, you go, when am I going to ever use this? I don't know why this is relevant. So it actually is here. If you haven't had calculus, then you might want to go check your Instagram account for a while, because this isn't going to make a whole lot of sense to you, and I won't make you know this for the test. But for those that have had calculus, I think that this will actually be something relatively important. So the rate of the disappearance of reactant A per time equals a constant if it's zero order kinetics. What I'm going to do is I'm going to move the negative sign to the other side of the equation and bring the dt to the other side of the equation. Now what I can do is I can integrate both sides of this equation. So now let's see if you know your integration. The left side of the equation is just the integral dA. There's no substance in front of it. It's just like the number 1. So if you had the number 1 dx and you were integrating that, what's the integral of 1 dx? That would just be x. So here the integral of 1 dA would just be the concentration of A. On the right side of the equation, we're taking the integral of negative k dt. What if you were taking the integral of negative k dx? Well, the integral of that would be negative kx. So in this case, when you take the integral of negative k dt, it'll be negative kt. So integrating both sides of the equation, I get concentration of A equals negative kt. Now this is a definite integral. I want to integrate from 0 to t, and so I'm going to evaluate these sides from 0 to t, which just means I take the concentration of A at time t and I subtract the concentration of A at time 0. On the right side, it's going to be the negative kt at times t minus negative kt at time 0. In this case, on the very right side, that very last term there, the negative k times 0, that's just going to be 0, so I'm going to leave that out. So really, when we integrate our rate law, we wind up getting an equation that says the concentration of A at times t minus the initial concentration of A must equal negative kt. If I add the initial concentration of A to both sides of the equation, I have this relationship, which is the equality statement we started the lecture with. Concentration of A at time t is going to equal negative kt plus the initial concentration of A. So this is an equality statement that's always going to be true for zero order kinetics. Now, what if the rate law for this reaction was rate equals K times concentration of A to the first power? In this case, this is a first order reaction, and we would abbreviate that by writing 1 with a not sign above it. That's read first order. And when you want to write a first order reaction rate, just like we have the rate law above in green, I could be more specific with the word RATE. What is that? That's the rate of either appearance of B or the disappearance of A. So the way we write the disappearance of A is we go negative D of concentration of A per small unit of time dt. So this is our first order rate law, just with rate written explicitly in terms of the reactant A. Let's do some calculus on this and show you where we get the equality statement. I'm going to move the negative sign and the dt over to the right side of the equation, and then I'm going to wind up integrating both sides of this equation. So now on the left side, we're integrating 1 over A dA. So think about, what do you get when you integrate 1 over x dx? You get natural log of x. So the integral on the left side of the equation is going to be natural log of A. On the other side, when I take the integral of negative kt, I'm just going to get, once again, negative kt. So integrating a first order rate law, I get natural log of A equals negative kt, and evaluating it from t to 0 is going to be the natural log of A's concentration at time t minus the natural log of A's concentration initial equals negative kt minus negative k times 0, which just disappears. So we get this relationship here. And if I add the natural log of initial concentration of A to both sides of the equation. I have the equality statement we started the lecture with for first order kinetics, and that is the natural log of the concentration of A at times T will always equal the negative KT plus the natural log of the initial concentration of reactant A. Now, if I take that equality statement that we've just determined for first order kinetics, and I raise it to E as a base, we'll have a related equation. Now, E raised to the natural log of concentration of A at time T just equals the concentration of A at times T. On the right side of the equation, when you go E to the negative KT, you get E to the negative KT. And when you go E to the natural log of initial concentration of A, you just get the initial concentration of A, but it's going to be multiplied by E to the negative KT. So this expression can be rewritten like this. If I raise it E to the base and raise all that to E as a base, and if I bring my A naught in front, if I just reverse the positions of the two factors on the right side of the equation, I have the concentration of A at time T equals the concentration of A initially multiplied by E to the negative KT. That should look familiar to you because we've seen that equation earlier in the semester. Remember where that's from? That is the radioactive decay equation. So if you remember, the number of radioactive isotopes at time T, which we abbreviate as N, will always equal the initial amount of radioactive isotopes, N naught, multiplied by E to the negative KT. That means radioactive decay follows first order kinetics. And we maybe didn't use that yellow equation exactly because we didn't have specific rate constants for different radioisotopes. We had half-lives for different radioisotopes. So we learned a little relationship that the specific rate constant K equals the natural log of 2 over the half-life. So when we did radioactive decay calculations, we substituted out the specific rate constant for natural log of 2 over the half-life, and this is the expression we used. But I just wanted to point out to you how that equation we used earlier in the semester is an example of first-order kinetics. Now, for this reaction one final time, what if the rate law for this reaction was rate equals K times concentration of A to the second power? Well, this is then a second-order reaction, abbreviated 2 with a superscript naught. And so the rate of the reaction, if we express it in terms of the disappearance of reactant A, is going to be negative D concentration of A over dt equals K times concentration of A squared. So this is our rate law. I want to do a little calculus on this and show you where its equality statement comes from. So if I move the dt and the negative sign over to the right side of the equation, I have D concentration of A over concentration of A squared equals negative K dt. And if I integrate both sides of the equation, now on the left side, I'm integrating 1 over A squared dA. And that's really like A to the negative 2 dA. How do you integrate that? You raise the exponent by 1 from negative 2 to negative 1, and you bring the reciprocal of negative 1 in front as a coefficient. So this is going to wind up being negative 1 multiplied by A to the negative 1 power, or negative 1 over A if you want. The other side of the equation is just going to be negative KT again. So once again, the integral of 1 over A squared is going to be negative 1 times A to the negative first power, or negative 1 over A. And then on the right side, the integral of negative K dt is just negative KT. To evaluate this from time t to time 0, it's going to be negative 1 over concentration of A at times t minus negative 1 over the initial concentration of A equals, it's going to be negative KT minus a negative K0. I'm just going to leave off the negative K0. And if I add to this equation, I add the negative 1 over A naught to both sides of the equation, I will wind up having negative 1 over A at times t equals negative KT minus 1 over A initial. And if I multiply the entire equation by negative 1, so I get rid of all those negative signs, then I wind up getting the equality statement we had earlier for second order kinetics, which is 1 over the concentration of reactant A at times T must equal KT plus 1 over the initial concentration of reactant A.